Step into the Coliseum of Cambridge exams, where the clock is ticking, the pressure is crushing, and only the absolutely most prepared survive. Welcome to This Explainer. I am your host, and today we are conquering one of the most notoriously brutal, heavily weighted topics in the entire computer science syllabus: adding, editing, and deleting data, from stacks, queues, and linked lists. I want you to picture the exam hall. You turn the page, and there it is, a massive past paper question asking you to insert a node into an ordered linked list. It is high stakes. Now I want you to imagine two typical students facing this exact challenge. First, there's Alex. Alex is the kind of student who overloads his answer with raw computer science facts. He memorized the textbook, sure, but he provides absolutely zero analysis and zero logical flow. He tries to update his pointers in the exact wrong order, and he entirely breaks the linked list in memory. Data is lost forever. Then we have Sam. Sam just rushes. He completely misses the specific command word requirements, completely ignores the crucial edge case where the list might already be empty, and just draws a messy, incomplete diagram on the page. You can guess what happens next. Both of their answers are returned as a sea of red pen marks. They failed to survive the arena. Their mark potential dropped to zero. But here is the good news. By the end of this explainer, you are going to possess the exact step-by-step blueprint to avoid their fate and secure those top-tier marks. Now look at this incredible quote directly from the source. The examiner's warning here comes with absolute, non-negotiable certainty. This topic is completely unavoidable. The principal examiner reports explicitly state that this topic appears in every single examination series. You literally cannot hide from it, so we absolutely have to master it. And listen, mastering it doesn't just mean rote memorizing some code snippets. It means developing a deep intuitive understanding of the mechanics behind dynamic data structures. Think about what is actually happening under the hood. When you push data onto a stack, you are dealing with a strict last-in, first-out architecture. The last item in is the first one out. When you enqueue data into a circular queue, you are managing first-in, first-out logic, but it's more complex than that, right? You are actively calculating wrapping rear pointers so you don't run out of memory space. When you delete a node from a linked list, you are carefully, systematically rerouting pointers to bypass the deleted data without losing the entire rest of your data chain. The Cambridge examiners know exactly how complex this is, which is exactly why they test it so rigorously. They are hunting for the students who really get it.
So if you are currently tackling the Cambridge AS and A-Level Syllabus 9618, you need a precise, standardized system to survive. But let's be real. Even if you are currently building your foundations in the lower-level Cambridge syllabuses like 0417, 0478, 0983, 0984, or 2210, the logical thinking required here is exactly what you are building towards. The 96018 syllabus in particular is incredibly unforgiving. It demands that you not only write the algorithms, but that you physically trace them, evaluate their efficiency, and adapt them on the fly to completely unfamiliar real-world scenarios. You simply cannot walk into this coliseum hoping your basic foundational understanding of simple 1D arrays will somehow carry you through. It won't. You need a highly tactical strategy that specifically targets the exact method marks the Cambridge grading scheme is waiting to award you.
To get you there, we will follow this structured, 5-part playbook. This is exactly what top-performing students do differently. 1. Core theoretical principles. 2. The procedural framework. 3. The method mark strategy. 4. Top examiner warnings. And 5. Critical analysis mastery. Let's jump straight in. Section 1. Core theoretical principles, where we build your architecture of success from the ground up. Building that architecture requires a total mindset shift. You have to stop viewing stacks, queues, and linked lists as just abstract concepts and start viewing them as highly specific tools designed to solve specific data flow problems. This brings us to a concept that Cambridge specifically calls connected understanding. They want to see your ability to link precise definitions and causal relationships to unfamiliar contexts. And how do the top 1% of students achieve this analytical depth? They use the PEAL framework. That stands for point, evidence, explanation, and link. Let's say a 9618 exam question asks you to evaluate the use of a linked list versus a 1D array for implementing a dynamic queue. Your point is your initial clear argument. Your evidence is a hard technical fact. For example, the fact that linked lists use dynamic memory allocation. Your explanation details the why, how this dynamic allocation actively prevents memory wastage when the queue size fluctuates. And finally, your link ties it directly back to the highly specific scenario in the exam prompt. This perfectly maps out the causal relationship of the pointers and proves to the